Understanding solar storms and their impact on Earth's power and communication systems. Imagine waking up one day to a world without the internet, GPS, or functioning phones, plunging humanity into chaos. This is not merely the plot of a science fiction movie, but a plausible scenario if Earth were to be impacted by a powerful solar storm. Solar storms are among the most powerful and impactful astronomical phenomena ever observed by humanity. These events occur when the Sun releases vast amounts of energy and charged particles into space, triggered by dynamic activity on its surface. A solar storm typically comprises two key components: intense radiation emitted from solar flares and coronal mass ejections, CMEs, both closely tied to the unstable magnetic fields of the Sun, the central star of our solar system. Solar flares are darker regions on the Sun's surface, where highly compressed magnetic fields become unstable. These flares release immense energy in the form of X-rays and ultraviolet radiation, significantly impacting the surrounding space. Concurrently, CMEs occur when plasma, a mix of ionized gas at extremely high temperatures, is ejected from the Sun at astonishing speeds, sometimes reaching 3,000 kilometers per second. According to NASA, a single CME can carry billions of tons of material with energy equivalent to millions of nuclear bombs, capable of altering the space environment near Earth. The Sun's activity follows an approximately 11-year cycle, alternating between periods of high activity and relative calm. During the peak phase of this cycle, the number of solar flares and CME events increases significantly, raising the likelihood of strong solar storms. These storms can have profound effects on space and Earth-based technologies, including disrupting the planet's magnetic field, interfering with satellite signals, and, in extreme cases, causing irreparable damage to electronic systems. The effects of solar storms are not confined to space, but also directly impact Earth and modern technology. When charged particles from solar storms collide with Earth's magnetic field, they can trigger geomagnetic storms that disrupt power grids, GPS systems, and satellite communications. A well-known example is the Carrington event of 1859, where an exceptionally strong solar storm crippled global telegraph networks and produced dazzling auroras visible as far from the poles as tropical regions. This underscores the importance of studying and predicting solar storms to mitigate potential risks. In recent years, space missions such as SOHO, Solar and Heliospheric Observatory, and the Parker Solar Probe have provided critical insights into how solar storms form and propagate. Scientists use data from these missions to improve space weather forecasting, enabling authorities to implement protective measures, such as placing satellites in safe mode or temporarily shutting down sensitive systems. Advancements in this research not only safeguard modern technology, but also ensure the safety of astronauts working in space. Understanding solar storms also provides a clearer picture of the relationship between the Sun and the planets in the solar system. These phenomena are compelling evidence of the Sun's power and dynamism, emphasizing the importance of maintaining and expanding space observation programs. Future research into solar storms will not only help humanity protect Earth from their dangerous effects, but also unlock further mysteries of the universe. How do solar storms affect Earth's magnetic field? When solar storms occur, they generate powerful streams of charged particles that speed toward Earth at millions of kilometers per hour. Upon interacting with our planet's magnetic field, these streams of particles not only engage with atmospheric layers, but also cause geomagnetic storms, a significant disturbance in Earth's magnetic field. The magnetic field, which serves as a natural shield against cosmic radiation, becomes destabilized when struck by particles from solar storms. Geomagnetic storms are not just complex physical phenomena, they also produce significant consequences that impact both the natural environment and human life. During geomagnetic storms, Earth's magnetic field undergoes intense fluctuations, leading to phenomena we often recognize as auroras, the colorful lights seen in polar regions. However, behind this mesmerizing beauty lies a concerning reality. Geomagnetic storms can disrupt modern technological systems that our society heavily depends on. Specifically, they can interfere with GPS signals, affect satellite operations, and even damage high-voltage power lines. This occurs because charged particles from solar storms, upon colliding with Earth's atmosphere and magnetosphere, can generate powerful induced currents across the planet's surface. These currents have the potential to overload electronic devices and cause severe damage to infrastructure systems. One prominent example of solar storms' impact on Earth's magnetic field and technology is the Carrington event of 1859, the largest solar storm ever recorded in history. During this event, an enormous coronal mass ejection, CME, struck Earth directly, triggering intense geomagnetic storms. Auroras were so bright that they were visible even in tropical regions, leading many to mistake them for sunlight at dawn. However, its effects extended far beyond this natural spectacle. The storm severely disrupted the global telegraph system, the most advanced technology of the time. Telegraph wires sparked, telegraph stations were destroyed, and many telegraph operators received dangerous electric shocks while working. More recently, in 1989, another solar storm caused significant damage in Quebec, Canada. Induced currents from the geomagnetic storm overwhelmed the power grid, resulting in widespread blackouts that affected millions of people for several hours. The economic loss from this incident was estimated to be billions of dollars, not to mention the indirect impacts on people's lives and regional economic activities. In addition to power grids, geomagnetic storms also significantly impact Earth-orbiting satellites. Although satellites are designed to operate in the harsh conditions of space, they remain vulnerable to high-energy particles from solar storms. Increased fluxes of charged particles can heat and expand the upper atmosphere, causing satellites to encounter greater drag, which can lead to orbit deviations or reduced operational lifespans. Furthermore, GPS signals, a technology we rely on daily for navigation and positioning, can be disrupted or completely lost during strong geomagnetic storms. This poses particular risks to the aviation industry, maritime navigation, and military operations, where GPS accuracy is critical. Electronic devices on the ground are not immune to these effects either. Transformers, power grid control systems, and even medical equipment in hospitals can be damaged by induced currents from geomagnetic storms. This is why experts emphasize the importance of strengthening infrastructure against the risks posed by cosmic phenomena like solar storms. Looking at the bigger picture, Earth's magnetic field acts as a shield protecting us from harmful cosmic impacts. However, when struck by solar storms, this protective layer becomes unstable, triggering complex reactions that affect both the natural environment and technological systems. While we cannot prevent solar storms, understanding them better allows us to mitigate risks and safeguard critical systems and lives on Earth. The Carrington event and the 1989 solar storm are just two striking examples of the immense power of solar storms and their far-reaching impacts on Earth's magnetic field. They serve as reminders that, in a world increasingly reliant on technology, we cannot ignore the threats from outer space. We must continue researching and developing protective measures to ensure that future geomagnetic storms do not disrupt humanity's rhythm of life. Did you know that the Sun, the star that sustains life on Earth, does not always maintain a steady activity level. In fact, it undergoes intense activity cycles, sometimes powerful enough to influence the entire solar system, disrupting communications, navigation, and even altering Earth's weather. The Sun's activity cycles. The Sun is not as stable as it appears on the surface. Instead, it experiences activity cycles lasting approximately 11 years, divided into two main phases: the active phase, known as the solar maximum, and the quieter phase, known as the solar minimum. These cycles reflect the complex changes in the Sun's magnetic field, a key driver of the dynamic phenomena on its surface. During the solar maximum, the Sun's activity reaches its peak. The number of sunspots, regions of intense and unstable magnetic fields, significantly increases on its surface. These sunspots are not just physical manifestations of magnetic turbulence, they also serve as sites for massive energy eruptions. These eruptions include X-ray flares, intense ultraviolet radiation, and coronal mass ejections, CMEs, plasma bursts ejected into space at speeds reaching millions of kilometers per hour. According to NASA, the frequency of CMEs during the solar maximum can increase up to tenfold compared to the solar minimum, leading to more extreme space weather phenomena. Conversely, during the solar minimum, the Sun's activity significantly diminishes. The number of sunspots decreases drastically, the solar surface appears more tranquil, and events such as geomagnetic storms and CMEs become rare. However, this does not mean the Sun goes completely dormant. The solar wind, although weaker, continues to influence Earth's magnetic field. Additionally, cosmic radiation from deep space increases due to the Sun's weakened magnetic shield, posing unique challenges to space missions and satellite technology. The study of the Sun's activity cycles dates back to the 17th century, when Galileo first observed and documented sunspots on its surface. However, it was not until the 19th century that scientists discovered the cyclical nature of these phenomena. Since then, astronomers have continually studied these magnetic variations to better understand their effects on Earth. Modern technology, such as the SOHO, Solar and Heliospheric Observatory, satellite, has significantly advanced the monitoring and forecasting of solar activity changes. Thanks to data from SOHO and missions like the Parker Solar Probe, scientists can now make more accurate predictions about the timing and intensity of major solar energy events. The Sun's activity cycle is not just an intriguing astronomical phenomenon, but also critically important to Earth and modern technology. During the solar maximum, intense radiation events and CMEs can have significant consequences, ranging from satellite signal disruptions and GPS inaccuracies to powerful geomagnetic storms capable of overloading global power grids. On the other hand, during the solar minimum, increased cosmic radiation from deep space can affect astronauts' health and the durability of equipment used in long-term space missions. A deeper understanding of the Sun's activity cycle enables humanity to not only anticipate and mitigate its negative impacts, but also explore the intricate relationship between the Sun and the planets of the solar system. Research into this cycle not only helps protect modern technological systems, but also expands our knowledge of how the Sun functions and influences the broader universe. Continued observation and study of the Sun's activity cycle will be crucial in ensuring the safety of Earth and future space exploration missions. Solar activity and space weather. The Sun's activity cycle has a profound impact on space weather, especially during the active phase, or solar maximum. As the Sun enters this period, its surface becomes highly turbulent, with a sharp increase in sunspots, regions of extreme and unstable magnetic fields, leading to the release of enormous energy. These phenomena generate solar winds laden with high-energy charged particles, accompanied by powerful CMEs. Consequently, the intensity and frequency of geomagnetic storms during this phase rise significantly, causing major fluctuations in Earth's magnetic field. The impact of geomagnetic storms during the solar maximum extends beyond Earth's magnetic field, directly affecting technological systems on Earth and in space. One of the most noticeable consequences is the disruption of satellites and GPS systems. According to the European Space Agency, ESA, dozens of severe geomagnetic events can occur each year during a solar maximum. These events degrade GPS signal accuracy, disrupt telecommunications, and, in severe cases, cause irreparable damage to satellite electronics. The effects of these storms can last from several hours to several days, depending on their intensity. However, even when the sun transitions into its quieter phase, the solar minimum, space weather does not entirely settle down. During this period, phenomena like cosmic rays from deep space become more pronounced due to reduced solar activity. The sun's weakened magnetic shield allows more intense cosmic rays to penetrate the solar system. This poses risks not only to satellites, but also to the health of astronauts on long-term space missions, particularly those venturing beyond Earth's magnetosphere. A notable example of space weather effects during the solar minimum occurred in 2009 when cosmic radiation levels reached record highs. This increase posed significant threats to satellites and astronauts aboard the International Space Station, ISS. Astronauts were forced to limit their activities outside the station and retreat to better shielded areas to minimize radiation exposure. This scenario underscores that both phases of the sun's cycle, solar maximum and solar minimum, have substantial impacts on space weather and human activities in space. Additionally, the sun's activity cycle profoundly influences Earth's magnetosphere. During the solar maximum, the magnetosphere becomes more compressed due to strong solar winds, resulting in larger geomagnetic storms and increased risks for terrestrial power grids. Meanwhile, during the solar minimum, although large-scale eruptions are less frequent, heightened cosmic radiation increases the likelihood of damage to sensitive electronic circuits. Understanding the sun's activity cycle and its impact on space weather is vital for protecting Earth and supporting space operations. Missions like SOHO and the Parker Solar Probe provide essential data for accurately predicting the timing and severity of these phenomena. This enables scientists and engineers to develop preventive measures, from shielding satellites to enhancing the resilience of power grids and ensuring astronaut safety. The effects of the sun's cycle on space weather highlight the complex interplay between the sun and the planets in the solar system. Regardless of the phase, these phenomena demonstrate the power and influence of the central star. Continued research into the sun's activity cycle not only deepens our understanding of space weather, but also aids in developing sustainable solutions for protecting technological systems and space missions in the future. Solar activity and the solar system. The sun's activity cycle influences not only Earth, but also the entire solar system, depending on each planet's magnetic field and atmospheric protection. Planets without strong magnetic fields, such as Mars and Venus, experience direct and severe impacts from solar winds, especially during the solar maximum. According to data from NASA's MAVEN mission, solar winds during this period have continuously eroded Mars's atmosphere, contributing to its transformation from a wet, potentially habitable environment into a cold, barren desert. In contrast, planets with robust magnetic fields, such as Jupiter and Saturn, effectively counter solar winds while producing unique astronomical phenomena. Jupiter's powerful magnetic field not only shields the planet, but also affects its moons, creating spectacular auroras. Observations from the Juno spacecraft in 2017 captured auroras on Jupiter that were far brighter than those on Earth, especially during the solar maximum. These phenomena showcase the strength of magnetic fields and provide valuable data on interactions between solar winds and planetary magnetospheres. On Earth, the Sun's activity cycle leaves a distinct imprint, particularly in polar regions, where the magnetic field is weaker and more vulnerable to charged particles from solar winds. During the solar maximum, auroras become more intense and frequent, creating dazzling natural light displays. However, not all effects are positive. Increased radiation in polar regions during this phase can pose health risks to individuals working in those areas, such as astronauts or researchers at polar stations. Additionally, heightened radiation levels present challenges for technological systems, including satellites and global communication networks. Beyond space phenomena, the Sun's activity cycle also influences Earth's climate. Some studies suggest that prolonged solar minimum phases, such as the Little Ice Age in the 17th century, were associated with slight global cooling, particularly in the northern hemisphere. This phenomenon may be linked to reduced solar radiation reaching Earth's surface, altering global climate patterns. While the relationship between the Sun's activity cycle and climate change remains an area of ongoing research, it is clear that these fluctuations can contribute to long-term planetary climate shifts. The interplay between the Sun's activity cycle and the planets in the solar system demonstrates the power of the central star. From gradually stripping away Mars's atmosphere, to generating brilliant auroras on Jupiter, to influencing Earth's climate and magnetic field, the cycle underscores the profound connection between the Sun and its surrounding planets. Continued research into these phenomena not only enhances our understanding of the relationships within the solar system, but also supports efforts to protect Earth from potential impacts and guide future space exploration missions. How can humanity confront an invisible yet formidable threat from the cosmos? Solar storms capable of disrupting the entirety of modern civilization. Scientists are racing against time to develop technologies to predict and mitigate their impact, safeguarding the planet from what seems like an unstoppable adversary. Predicting solar storms. In addressing solar storms, accurately predicting when and where they will occur is the first and most crucial step. Space observatories like SOHO, Solar and Heliospheric Observatory, and SDO, Solar Dynamics Observatory, play pivotal roles in this mission. These advanced telescopes continuously monitor the Sun's surface, focusing on sunspots, regions of strong and unstable magnetic fields where major energy eruptions typically originate. Launched in 1995, SOHO was one of the pioneering instruments for studying the Sun. It has provided thousands of detailed images and data on coronal mass ejections, CMES. According to NASA, SOHO records hundreds of CME events annually, contributing significantly to our understanding of solar wind patterns and the ability to predict geomagnetic storms. By tracking changes on the Sun's surface, SOHO has become a reliable watchdog, issuing early warnings that help minimize risks to technological systems and satellites. Meanwhile, SDO, launched in 2010, has taken solar observation to a new level. With its exceptionally high-resolution imaging capabilities, SDO captures detailed views of the evolution and dynamics of sunspots and energy bursts on the Sun's surface. The data from SDO provides crucial insights into the speed, temperature, and density of charged particles, enabling scientists to make more precise predictions about how they will interact with Earth's magnetic field. With its continuous monitoring, SDO serves as a bridge between theoretical research and practical applications in protecting modern technological systems. Another breakthrough in solar storm research and prediction comes from the Parker Solar Probe, the first spacecraft to approach the Sun's surface. Launched in 2018, the Parker Solar Probe has surpassed all previous limits. venturing into regions of space never before explored. The probe has collected unprecedented data on the solar wind, how it accelerates and spreads into space. Findings from the Parker Solar Probe not only unravel the mechanisms behind solar storms, but also offer deeper insights into their origins and characteristics. This opens up significant opportunities for earlier and more accurate space weather forecasting. Beyond observatories and probes, combining data from multiple sources is gradually enhancing solar storm prediction capabilities. International programs like the International Space Weather Observation System, ICES, connect research centers and observatories worldwide to share real-time data and issue timely alerts. This information not only helps protect satellites, power grids, and other technological systems, but also ensures the safety of astronauts on space missions. Solar storm prediction technology is not just a scientific achievement, but also an essential tool for mitigating risks from space weather. From SOHO's early observations to the groundbreaking discoveries of the Parker Solar Probe, every advancement brings humanity closer to understanding and effectively responding to the powerful phenomena originating from the solar system's central star. These technologies not only protect Earth, but also lay the groundwork for further advances in space exploration. Early warning systems. While predicting solar storms is critical, implementing effective early warning systems is what truly helps mitigate the risks associated with these phenomena. In the United States, the Space Weather Prediction Center, SWPC, part of NOAA, plays a central role in monitoring and issuing alerts about space weather events. Using data from satellites and observatories, this system tracks charged particle flows and CMEs. When a significant CME event likely to impact Earth is detected, SWPC issues timely warnings. These alerts are particularly valuable to industries reliant on satellites, such as aviation, telecommunications, and energy, giving them time to take preventive measures. In addition to SWPC, international space agencies like NASA and ESA contribute significantly to enhancing the effectiveness of early warning systems. ESA's Space Weather Coordination Center, SSCC, is a prime example. This center operates as a global network, integrating data from multiple observatories and satellites to provide detailed analyses of space weather. Collaboration between international agencies significantly improves accuracy and reduces warning times to just a few hours. This time frame is sufficient for critical infrastructure, from power grids to satellite systems, to implement protective measures in time. One sector that directly benefits from early warning systems is aviation. Flights traversing polar regions, where Earth's magnetic field is weaker and more vulnerable to radiation, often need to adjust routes when solar storm warnings are issued. According to reports from the International Air Transport Association, IATA, such adjustments reduce radiation exposure risks for passengers and crew while ensuring flight safety. Although these measures may increase costs and travel times, they are essential for protecting human health in the harsh conditions of space. Satellite telecommunications and GPS systems also benefit from early warning systems. Upon receiving alerts from centers like SWPC or SSCC, satellite operators can temporarily disable or switch satellites to safe modes to avoid damage from high-energy particles. This reduces the risk of data loss and protects costly equipment from long-term damage. Similarly, terrestrial power grids can be safeguarded by reducing load or disconnecting parts of the system during signs of strong geomagnetic storms, mitigating the risk of overloading or transformer fires. Another noteworthy aspect of early warning systems is their role in ensuring the safety of space missions. On the International Space Station, ISS, astronauts rely on warning data to adjust schedules for spacewalks, avoiding high radiation exposure during intense solar storms. Thanks to timely warnings, astronauts can shelter in well-protected areas, minimizing long-term health risks. Collaboration among international organizations and the use of advanced technology and early warning systems have significantly improved global responses to space weather challenges. Programs like SWPC, SSCC, and missions like SOHO and Parker Solar Probe provide critical data, not only enhancing predictive capabilities, but also increasing warning efficiency. These efforts protect modern technological systems while ensuring safety in key industries. Continued development and expansion of early warning systems will be key to addressing the growing challenges of space weather in the future. Mitigating the impact of solar storms. Beyond prediction and warnings, implementing measures to mitigate solar storm damage is essential for protecting critical infrastructure on Earth and in space. Modern satellites are designed with advanced shielding to minimize the effects of high-energy particles. They use special radiation-resistant materials and multi-layered structures to protect sensitive electronic circuits. For instance, SpaceX's telecommunications satellites are equipped with protective casings that extend their lifespan and ensure stable operation in the harsh conditions of space, which frequently face solar wind and cosmic radiation. For power systems, protective measures are implemented to reduce the risk of damage from geomagnetic storms. One common method is temporarily isolating sections of the power grid during periods of intense geomagnetic activity. This reduces stress on the system and protects key equipment like transformers from overloading. According to a study by the Institute of Electrical and Electronics Engineers, IEE, isolating circuits has proven highly effective in mitigating risks. For example, during the 2012 geomagnetic storm event, the U.S. power grid remained stable due to advanced protective strategies. In addition, artificial intelligence, AI, is being researched and applied to enhance the ability to mitigate solar storm impacts. AI algorithms are being developed to analyze and predict the effects of geomagnetic storms on specific regions with high accuracy. These models not only improve the effectiveness of preventive measures, but also optimize costs for maintaining and upgrading infrastructure. By providing more precise and detailed forecasts, AI supports system operators in making timely decisions, from adjusting power grids to protecting satellites and space equipment. Moreover, international companies and organizations are working closely to develop standards and methods for protecting global infrastructure from space weather impacts. For example, new satellite systems are designed not only to withstand radiation, but also equipped with real-time monitoring sensors that detect early signs of geomagnetic storms and automatically switch to safe modes when necessary. This minimizes the risk of irreversible damage while extending the lifespan of expensive technological devices. For industries relying on satellite systems, such as aviation and telecommunications, damage mitigation measures are also implemented in a coordinated manner. In aviation, polar routes are frequently adjusted to avoid solar storm radiation. This not only protects passengers and crew health, but also ensures safe flights under challenging conditions. In telecommunications, service providers implement safeguards such as temporarily disabling or switching satellites to safe modes to minimize data loss risks and maintain uninterrupted communication services. The combination of advanced technology and international cooperation has created a more effective prevention system against space weather threats. From building resilient satellites and applying AI to developing global standards, all efforts aim to protect critical infrastructure from the negative effects of solar storms. Continued research and application of these solutions not only ensure the safety of modern technology, but also enhance resilience against the growing challenges posed by the cosmos. Long-term strategies for solar storm mitigation. To effectively address the threats of solar radiation in the future, scientists are researching and implementing groundbreaking long-term solutions. One promising idea is the development of artificial magnetic shields, an advanced technology capable of generating protective magnetic fields around space equipment such as satellites and spacecraft. According to ESA, these shields could reduce up to 90% of high-energy radiation exposure, thereby extending the lifespan and ensuring the stable operation of equipment in harsh space environments. Artificial magnetic shields are not only significant for protecting satellites, but also play a crucial role in human missions to Mars. Since Mars lacks a natural magnetic field like Earth, solar radiation and cosmic rays on the planet pose significant dangers to astronauts and equipment. A proposed solution involves developing specialized shielding structures or using high radiation-resistant materials to protect humans and devices. According to NASA's 2020 research, without effective protective measures, radiation levels on Mars could be up to 50 times higher than on Earth, causing severe health damage to astronauts on long-term missions. In addition to magnetic shields, long-term plans focus on building more sustainable space infrastructure. One notable initiative is solar power stations in orbit, which can operate independently of Earth's energy systems, minimizing the impact of solar storms on critical energy sources. These stations could not only serve space equipment, but also provide energy to facilities on Mars or remote research outposts in the solar system, opening new opportunities for space colonization and exploration. Furthermore, enhancing the resilience of space equipment to radiation is part of the long-term strategy. Future satellites and spacecraft will feature specialized protective layers and sensitive sensor systems, enabling them to automatically detect and adjust to high-energy particle streams. This reduces the risk of damage and ensures more stable operation over time. For deep space missions, where radiation levels are much higher than in Earth's orbit, solutions such as constructing bases beneath planetary surfaces or using water as a radiation shield are being considered. Water, with its excellent radiation absorption properties, could serve as both a vital resource and a natural shield to protect astronauts. This is a promising idea for bases on the Moon or Mars. Long-term strategies also involve using AI to predict solar storm events more accurately and assess their impacts on specific areas. This allows for rapid and effective implementation of protective measures, from adjusting spacecraft trajectories to safeguarding critical energy systems. These initiatives aim not only to minimize the effects of space weather, but also to advance space technology in the future. By investing in sustainable and groundbreaking solutions, humanity can protect modern technological systems while laying a solid foundation for expanding its presence in the solar system. This represents a significant step toward conquering space and ensuring safety for future generations.